I'm pleased to welcome Dr. Sue Hovorka and Dr. Ramanan Krishnamoorti here. Dr. Hovorka is at the University of Texas at Austin, and Dr. Ramanan Krishnamoorti is at University of Houston. I apologize if I butchered your name. And so we've heard a couple of questions already. There's just I think it would be very helpful to start with just the very basics. When we say carbon capture and storage, what are we talking about? You heard Reverend Caldwell, you heard some of the questions that were just raised. Let's start with the basics. What is this? And then let's go from there. Where are we putting the CO2? How deep underground is it? And then we can expand. So, Sue, I'll pick on you first. And I'll give you, do you have a mic? Great.
Make the light turn green. Okay.
And keep the mic close to your mouth so everyone can hear you.
So let's answer these questions. The carbon capture is to catch the CO2 before it goes in the atmosphere, or to remove it from the atmosphere. And we have a lot of tech. We talked about that yesterday. Where it goes after it's been captured is back where it came from. It was in residence in the earth, either in agricultural lands or in fossil fuels or in limestone, and it needs to be put back. We don't want it loose in the atmosphere. We don't want it loose in the ocean. So we put it back to where it's supposed to be. We do this by deep well injection, which we heard yesterday is permitted. We have a permitting rules that are online. They're set up by the Environmental Protection Agency, and it's called the Underground Injection Control Program. So if anybody wants to know what the rules are, they've existed since the 70s and been operated in many states for many thousands of wells. And the rules are, and what EPA has is very accessible. You can read about it. So it has to go below the freshwater and has to protect the freshwater. The core thing of the program is to isolate CO2 from drinking water. So drinking water in Texas is at about 2,000 feet deep, so it's quite deep. So it has to go deeper than that, and it has to be below that. So we usually inject CO2 in most of these projects that you hear about at about a mile, someplace between 1 mile and 2 miles deep. The parish plant, in particular, goes to West Ranch and is injected at 8,000 feet. And I actually personally was involved in my team monitored that for the security. So I'd be glad to tell you what we did and how we did it.
Dr. Hovorka, I wonder if you could just describe, so we inject CO2 as a gas. We're compressing it. We're putting it underground. What happens when it's down there?
So
is it just bubbles? I mean, paint a picture. What is going on?
I was going to bring you some CO2, but I didn't get. I had trouble with Houston traffic from Austin, so you guys overwhelmed me. I couldn't get the CO2 here, so you could see it. It goes. It's captured as a gas, but it has to be compressed to be handled. We have to push it that far underground so that but the point at which it is at sufficient depth, it becomes a dense liquid-like phase. It's a little too warm to be officially a liquid, but it's a liquid. If you imagine it as a kind of runny liquid, you'll be thinking about it right. It goes into spaces in sedimentary rocks. So don't imagine big open spaces. Don't imagine caves. Don't imagine a place you could get to. It's in the spaces between the grains, sand in this area, the sand grains of the rock. To make this really vivid for you, you've been take yourself to the beach, and you have a big green drink, and you spill it. Where does it go? It goes in between the sand grains of the beach. And can you get it out with your towel? Can you suck it out with the straw? No. It gets stuck between the sand grains. That's what happens to it when it goes underground.
The other place that you could do it is into saline aquifers, right? So you could also.
That's what I meant. We were talking about this. So we say saline and aquifer, which confuse people. Yep. People think that saline is salt. We're not putting it in salt. And people, we say aquifer, and you say, well, I want to drink that. So when we say saline aquifer, please translate this to techno speak, not clear.
Exactly.
So we put it into rocks that are full of salty water that's too salty to be used. That's isolated from fresh water by law. It has to be, and it's isolated by physics too. So.
Dr. Krishnamurti, would you like to?
So imagine that I've got about 4,000 liters of CO2 up under atmospheric conditions. So it's something that comes out of those stacks. I've got 4,000 liters. By the time I compress it and put it underground to where Sue was talking about, it becomes a liter. That's how much compression it goes under, and that's why it feels like a liquid there. And so don't think of this as being just gases that are just floating around. These are more like water. They're almost as dense as water when they are in those deep aquifers. So they occupy barrel volume, which is why they can get between those rock, in the what we call the pores, the micropores, if you will, and that's where they reside. And primarily, they're not going to bubble. They're going to be. It's not like your Coke bottle, right? So your Coke bottle has CO2 in it, but when you open it, it starts to come out like bubbles. It's not going to happen that way. It stays there as a liquid. It stays there because the pressure that all that soil that's sitting on top of it keeps it there. And so it's not going to suddenly just release. Right? And so once it's there, it's going to sit in those pores.
So one of the main concerns we've heard yesterday, and I'm sure we've heard this elsewhere, is that question of pressure. We're injecting something down underground. We're increasing the pressure. And why should we think that it is safe to do that? When you add pressure, we all know things can, if you add enough, break, right? So why should we feel that we understand what's going on 1 mile down underground well enough that that we should feel comfortable about putting this underground in the way you've described?
I love being asked about pressure. It's one of my favorite topics.
And let's just be clear, Dr. Hovorka might be considered the mother of carbon management. So if there's anyone who knows the answer to this, it is the woman you see in front of you.
Now I can't talk.
I'm sorry.
So we have to push it down hard enough to push the aside the salt water that's in the place. And also we want to push a lot into a compact area. So pressure is important, but too much pressure is not allowed. It's not allowed by rule. The regulator will set the operator will propose, and the regulator will accept the maximum allowable pressure in the zone. And it's set by statute what it can be. It's below the strength of the rock. How do we know the strength of the rock? We actively test it by breaking it locally to the well. We go down to the well, we slam it with a water hammer, we slam it, we break it, then we know how strong it is. So it's absolutely necessary, but not particularly difficult to do. And you can ask when you're near a project, what the maximum allowable pressure is, and also how much surveillance they're doing on that. The operator, the pressure has to be reported. It's in the public record. You should be able to watch it and see that they're doing what they're supposed to be doing.
Dr. Krishnamurti, talk to us about surveillance. How do you survey what's happening 8,000 feet underground?
So we've been doing this for 100 plus years. We've been doing this we listen to what the ground is telling us, right? So we essentially put we put nice hearing aids on and essentially listen to what the ground is telling us. And what we can also do is we can also...
should we picture like somebody with their ear on the ground?
Pretty much you have a stethoscope, right? So just like a doctor sticks a stethoscope on you and listens to your body, that is almost identical to what we do when we are listening to what the ground is telling us. But we can do a little bit better, right? We can actually put a signal, just send a sound wave down and then watch it reflect back. And that reflection tells you a lot about what the structure is, where the liquids are, where the solid rock is, and is this liquid where you think it is. Right? This is how we've prospected for gas and oil over the last 100 years. We're now doing it in reverse. We're now turning around and saying, where might I be able to inject this CO2? And once I put it in there, will it stay where it is? And I can continue to monitor this over the next several years, actually several decades. And much of this, with sort of the advent of a lot of the digital technologies, the wireless technologies, these can be done on an ongoing basis and at almost no cost, no added cost with time. And so that's one of the big advantages.
Great. So I want to cover, we've thrown out, there are a lot of terms. There's a lot of terminology here. And I want to, get, before we conclude, a couple of definitions straight in our heads. So the terms that I'd love to clarify are carbon management. Like, what is that? CCS. What is CCS? How is it different? What is, so CDR, another C. CCS, CDR. And then we've got DAC, DAC. It's a lot to keep straight.
Lots of it. We've got a nice alphabet soup, but everything has C in it, right? And
right. So let's walk through it.
So what's our challenge? Our challenge is carbon. Carbon dioxide, carbon monoxide. So these oxides of carbon are the primary challenge that we sort of deal with.
And oxides mean carbon and oxygen together, like CO2.
And I make CO2, or I make carbon monoxide, which is really poisonous, right? So the one big fear we have at home is in winter time, making sure we don't have too much carbon monoxide being produced. So you have CO monitors present. So the whole issue in the burning of fossil fuels is the production of CO2 and carbon monoxide. So these oxides, and the reason they're a challenge is because they keep the warmth of that should be reflected back into the atmosphere back near the Earth. That's what we're trying to address. And so this whole idea is, how do I deal with these emissions? That's the broad landscape of what we call carbon management. And so and now we can start to talk about the rest of that alphabet soup, right? And the rest of that alphabet soup is, how do I implement carbon management? So the first one of those is what we call as carbon capture and sequestration,
CCS.
Or CCS, right? And so when we think carbon capture, we're thinking about places from which a high concentration of CO2 is being released from a single point. And so think of a power plant. Think of an ethanol facility where you're making ethanol, such as people making in Iowa or Michigan. Or think about where you make fertilizers. Every one of these places, you make a high concentration of CO2. You can go all the way down to chemical plants, which are on the low end of that high concentration limit. But there's still a single point, and I can apply simple chemical technologies to pull that CO2 out.
Right.
And that happens to be the place where I've got the lowest price for carbon.
And it makes sense it's the lowest price because it's the highest concentration of CO2, so the least energy or cost to pull it out. So we're talking about smokestacks. We're talking about point sources.
Exactly.
CCS.
So that's the reason why everybody's thinking about Houston, right? You've got the parish power plant. You've got lots of other natural gas-fired power plants. You've got large chemical refiners. You've got chemical manufacturers. Each of them has a point source of CO2.
So how's that different from DAC?
So now let's talk about a place which we all try and minimize, but we all do, right? Which is we drive a car. That car exhaust, what are you doing when you drive your car? Most of us, we take gasoline, we burn gasoline. And when we burn gasoline, we produce two things, carbon dioxide and steam, or water vapor, right? So the water vapor is perfectly fine. It goes, forms clouds, comes down back as rain, all fine. The other challenge is CO2. So when you look at what comes out of your exhaust, it's about 20% CO2. 20% by volume is CO2. Be great if I could somehow stick something to capture that CO2. We've tried it, right? It just your car becomes 3 times its weight, your fuel efficiency drops by a factor of 3. It's a pointless exercise trying to capture the CO2. But the moment that CO2 gets out of your car, it dilutes down to what the atmospheric level is. And so the atmosphere actually is a very good mixed, it really mixes very, very quickly. So back in my parlance as a chemical engineer, we call it a fantastic mixing reactor, right? So it really mixes and homogenizes really, really quickly. You get down to about, from 20%, you get down to 0.04%. So think about it, right? I've gone 3 orders, so it's dropped down by a factor of 2,500. And when that happens, it becomes much, much more difficult to take it out of the air. And that is the whole idea behind direct air capture, is that CO2 that's in, the carbon dioxide that's in the air at these very dilute concentrations, I'm trying to suck it out of the air.
So in our last moments here, paint a picture just so we all have a visual. Direct air capture versus CCS. When we think about direct air capture, what image should be in our head? What does that look like? How big is it? Give us a sense of what we're looking at. What does it sound like? Does it smell? Like, what's going on in front of us? Direct air capture first.
Direct air capture first, right? So what you will see is very large fans moving air as quickly as it can through a place that can actually take that carbon dioxide out of the air.
Stacks of fans.
Stacks of fans. And remember, to get 1 kilogram of CO2 from that direct air capture unit, I need to move 10,000 kilograms of air through. That is the challenge that many of us as engineers face. I got to move a lot of air through to get that amount of CO2.
So it's expensive, it takes a lot of energy, and so we have to make sure that if we're doing DAC, we're using green energy so that, right, so we're not adding CO2, on a net basis. But anyway, that aside, so then CCS, so what does that look like? Is it something that can just fit inside the smokestack? What does it look like in front of us if we were to look at CCS?
Now, you should see that picture that she had from the Parish power plant, right? The CCS unit that they have there, which captures 1/12 of all the emissions coming out of Parish, is almost as big as the power plant itself. So it's got a big footprint. And that's one of the big challenges with CCS, is it's got a large footprint. Engineers are trying to work on it to try and reduce that footprint. It's going to take some doing to reduce that footprint. Mm-hmm. But it is a pretty large footprint. It looks like a complex chemical unit that does it, but it can be done in a way that does not allow for additional emissions to come out.
And we're talking about a significant amount of that CO2 is captured. How much are we?
90 to 95% of that flue gas stream can be captured through a CCS unit.
We have one across the street from my office. Come see us in Austin if you want to visit one. We'll take you on a tour.
All right, and thank you so much, our panelists. I'm going to turn it back over to my colleague Emma, our managing producer at Climate Now, for the next panel, Community Engagement.